All right, let's dive right in. Today, we're going to unpack two of the coolest and, yeah, most confusing behaviors that waves have. We're talking about diffraction and interference, the secret physics that literally shapes everything you see and hear.
So, let's start with a few mysteries from your everyday life. I guarantee you've seen all of these, but you probably didn't realize they all share the same incredible, wave-based secret. You've totally seen this, right? You tilt the CD and bam, this shimmering rainbow just appears out of nowhere. That's not paint and it's not a dye. Nope, it's pure physics. It's what happens when light waves bounce off the thousands of microscopic little grooves on that disk.
Or how about this one? Sound just seems to bend. It wraps around corners and obstacles in a way that light, well, doesn't seem to. This is a huge clue that waves don't always march in perfectly straight lines. We're going to find out exactly why that is.
And this is what I find really interesting, because it kind of breaks a rule we all learned in school. We're told light travels in a straight line, right? But if that was 100% true, every single shadow would have a razor-sharp edge. That fuzziness you see? That's our proof that even light bends, just a little, as it sneaks past an edge.
So what's the secret? What ties together a rainbow on a CD, hearing someone around a corner, and fuzzy shadows? The answer, the common thread here, is all about how waves behave. And it boils down to two ideas that are super closely related, interference and diffraction.
Okay, to really get this, we've got to start with the first piece of the puzzle, interference. All this is what happens when two or more waves run into each other in the same spot at the same time.
Now, the absolute key phrase here is different sources. Think about dropping two pebbles into a calm pond. You get two sets of ripples spreading out. Where those ripples meet, they can either join forces and make a bigger wave, that's called constructive interference, or they can cancel each other out, leaving the water totally flat. That's destructive interference. That whole process is called superposition. And the most famous example of this ever is the double slit experiment. It's genius. You start with one wave. You send it towards a wall with two little slits in it. As the wave passes through those slits, it's like you've created two new, perfectly in-sync wave sources. And as those two new waves spread out, they interfere with each other, creating that classic pattern of bright and dark stripes on the screen behind it. It's beautiful.
Okay, now for our next concept, diffraction. If interference is all about different waves meeting up, you could say diffraction is a little more personal. It's about what a wave does all by itself.
Now, to get diffraction, you have to wrap your head around this one, kind of mind-bending idea called the Huygens-Fresnel principle. It says you should picture any big, single wave, like a beam of light, as being made up of a whole line of infinitely tiny point sources, and each one of those is sending out its own little circular wave or wavelet.
And that is the secret. When that line of wavelets hits an obstacle or goes through a slit, some of them get blocked. The ones that make it through keep spreading out and, here's the punchline, they start to interfere with each other. So really, diffraction is just what happens when a single wave gets in its own way and interferes with itself.
And this is what explains those fuzzy shadows. When light goes past an edge, it bends. When it goes through a single tiny slit, the wavelets from the top of the opening interfere with the wavelets from the bottom, creating its own distinct pattern. It's not as clean as the double slit pattern, but it's undeniable proof that waves bend and interfere with themselves.
Okay, showdown time. Let's put these two head to head. I know they sound similar, they often happen together, and they're super easy to mix up, so let's get this sorted out once and for all.
This is the big question, right? Are they actually two different things, or are they just two sides of the same coin? Well, the easiest way to see the difference is to look at where the waves come from and the patterns they end up making. Let's break this down. The most important difference is the source. For interference, you need at least two separate coordinated sources, like our two slits. For diffraction, it's just one wave interfering with itself. And that basic difference leads to everything else. See how interference fringes are all the same width with a really sharp contrast between bright and dark? Diffraction, though, it gives you that one big, bright central band with dimmer, fuzzier bands on the side. But now for the big reveal. Are you ready for this? Even with those differences, on the most fundamental level of physics, they're the exact same process. They're both just wave superposition. The only real differences are vocabulary.
You know what? Here's the simplest way to think about it. Interference is what we call it when you have just a few waves interacting, like a duet. Diffraction is what we call it when you have a continuum, basically an infinite number of tiny wavelets interacting. That's the full choir. It's the same physics, just at a different scale.
Okay, so waves bend and they collide. You might be thinking, cool story, but who cares? Well, you should, because these little effects have absolutely enormous consequences. They actually define the limits of what we can see, and they're the engine behind some of our most powerful technologies.
Seriously, just think about this. How sharp of an image can a telescope see? That is fundamentally limited by diffraction. The technology that allowed us to figure out the double helix shape of DNA, that's X-ray diffraction. And yeah, that awesome rainbow on a CD we started with, that's diffraction. From looking at distant galaxies to understanding the building blocks of life itself, these principles are everywhere.
And here's where it gets really, really weird. It's not just light and sound. One of the most shocking discoveries in all of physics is that particles, the tiny bits of stuff that make up matter, they also act like waves. You can actually shoot single electrons through a double-slit experiment, and I'm not kidding, they will create an interference pattern as if each electron went through both slits at once.
So we'll leave you with this final thought to chew on. If solid things like electrons can act like waves, what does that mean about the line between an object and a wave? The fact that everything, from light to sound to you, exhibits these wave behaviors, well, it forces us to ask some pretty profound questions about what reality is actually made of. Thanks for watching.